Screen can
We see it.
very good. All righty, so the topic today is to talk about antennas. So let's just go ahead and get started. Good evening. My name is Dave Wickard, AE7TD. So let's talk about antennas. First of all, there's a common theme in amateur radio that many of us feel that the entire hobby is misnamed. It shouldn't be called amateur radio. It should be called amateur antennas, because antennas are so important to the overall field and for you being successful. One of the things that you will find frustrating with ham radio operators is we use the terms wavelength and frequency as if they are the same thing, and we seemingly seem to shift back and forth at ease. This is something that you will get used to over time, that sometimes we'll talk about the 440 band, and then a second later we'll talk about the 70 centimeter band. And the reason why is because we're one of the few groups associated with radio that still needs to work with antennas. When I was in electrical engineering as a undergraduate getting my electrical engineering degree, I very, very seldom ever heard the word wavelength, but that's because I was into transistor design. And if I had been doing antennas, I would have heard the word wavelength in every class. And you're going to notice as we go forward with antennas that I'm going to say the word wavelength over and over and over again. So as an amateur radio operator, the reason why we intermix wavelength and frequency is because frequency may be what we deal with in the radio when you're setting up and configuring your radio, but wavelength is what you will use and will be of supreme importance to you when we start talking about antennas. Another reason why antennas are so important to us is because we're not dealing with a megawatt commercial radio station. When you have a 20 million watt AM station that is broadcasting at night, you don't need to worry about antennas because just about any size antenna will work for you. But when you're only looking at 100 watts or with your little HT, only 5 watts, then you need what we call a resident antenna. And a resident antenna is one that is designed, it's been optimized to work on particular bands that we want to work with. And so what I want to do is I want to talk about a little bit around why that is true with an antenna. So first of all, let's look at a single wire. So here's a single wire that you've just laid out across the ground. And there's a couple of things that we know about it. Number one, when you try to transmit on a radio signal, you'll notice that the current that moves in the wire looks like a wave, as you would expect. Electrical magnetic waves need a wave to be able to propagate, and that wave will the most important characteristic about the wave is that when all the way at the end of the wire, because there's nothing for the wire to be able to connect to, the one thing that you know will always be true is that the current at the end of the wire will be 0. And so you may bounce back and forth as the wave moves down the antenna, but at the end of the antenna, the end of the antenna will always be no current because the currents have nowhere to go. And so we can use Ohm's law and the power function to calculate the voltage and the power distribution along the wire using the power formulas that you talked about on the first day of the class. The second thing I want you to look at, so that's a single wire. Normally that's not necessarily important with amateur radio. There's a lot of shortwave listeners that love using long wires, and they'll just stretch a long wire as far as they can out across their property, and that's a fine antenna for them. It's not for us. So now let's transition to what I'll call ladder line. So here we have two wires that are one wire is connected to ground, and the other wire has the actual electric signal that you're trying to transmit on the other wire. The two important things to notice here is, again, the current at the end of the wire must be 0 because it's got no place to go. So the current at the end of this wire must be 0. And because the signal is on one side tied to ground and the other side tied to whatever transmitter we're using, you'll notice that the waves are exactly 180 degrees out of phase. So whenever one is up, the other one is down. When the one is up, the other one is down. And that means that this wave, as it propagates through the transmission wire, will always, one side will offset the other, and you'll have no loss of signal. So whatever comes in, if you were to hook this up as an antenna, whatever comes in at the feed point where the ladder line hooks up to the antenna, that's how much power will actually be transmitted, because with the transmission line, the currents offset the magnetic field around the antenna wire. So that's kind of interesting, but again, we're still not actually transmitting anything. So this next step is where the magic comes into play. So now what I'd like you to think about is we're going to take this same ladder line wire, and we're going to start bending back just a little bit of the wire, a little bit at a time. So we're going to bend back one wire, and then we're going to bend back the other wire just a little bit. Let's suppose it's just a 1/16 of the wavelength. Well, we have a nice wave that will propagate out the antenna, but it's still pretty small. If we keep making it a little bit larger and a little bit larger, and we fold it back to a quarter wavelength, then we get what actually turns out to be the maximum amount of current that would flow on the wires. And that's the reason why a dipole is a half wavelength in total length, 1/4 on one side and 1/4 on the other. And so when the wave propagates out from the dipole, it just bounces back and forth. If you were to go too much farther than a quarter wavelength, then what happens is you don't have the maximum amount of current flowing at the feed point. And if you get longer than half a wavelength, then the pattern that the antenna is actually transmitting will start conflicting with each other. So the optimal length of a dipole is a half a wavelength, regardless of what frequency you're transmitting on. So we talk about half wavelength dipoles. A quarter wavelength on one side and a quarter wavelength on the other side. That's the optimal antenna that we're going to design our antennas around. So now we can start looking at different types of antennas. Suppose we take this dipole and we rotate it 90 degrees so that it's vertical. You'll notice that the element that points up is a mirror of what points down. So what we can do is we can take the quarter wavelength wire that points down, and we can do a couple of things with it. We can try to replace that wire with a ground plane. And there's a couple of antennas that allow you to do this. Here is a very common, what's called a ground plane antenna, the antenna in blue. That's the antenna that you will see at a lot of base stations. Will have an antenna like that. It has a pole that sticks straight up, that's a quarter wavelength, and then it has a couple of different radials that point down at a 45-degree angle to act as the ground plane, the other half of the antenna. Another thing that you can do is you can mount the vertical element all the way on the ground, and lay out a bunch of vertical wires on the ground. So here is another kind of antenna. This is what an antenna called a vertical antenna that has a quarter wavelength pointing straight up in the air. And rather than a quarter wavelength pointing down, it has a radial field with a bunch of wires that have been tuned for a quarter wavelength for each of the bands that this antenna needs to be able to radiate on. So that's another kind of dipole that's been just modified just a little bit. Another common vertical that you will see will be a mag mount. This is a mag mount antenna that you would put on your car. And here the roof of your car is acting like a quarter of the wavelength. The mirror, that the ground plane that the wire is operating under, and then the wire, the element that points straight up in the air is a quarter wavelength. On 2 meters, a quarter wavelength is a half a meter. A meter is 39 inches, which means the vertical element that you're sticking up in your car is 19.5 inches. Did I stop sharing? Oh, am I still sharing?
Yeah, I can still see it.
Alrighty, very good. For some reason it went away on me. Give me just a second. Let me stop and restart sharing, sorry. Oh, here we go. All right, and a similar thing happens on your, whoops. All right, again, it's doing it. Similar thing happens on your little handheld, where you'd like your rubber duck antenna to be a quarter wavelength. And the ground plane is the metal frame of the radio that's inside the plastic. So this is actually like a dipole, but a quarter wavelength, which is the little rubber duck, and then the metal frame in the antenna, in the radio, acts as the ground plane. So this is a center-fed dipole that we've just been looking at all the time. Its impedance at the feed point where the feed line comes in is about 70 ohms. You can take that antenna and have what's called an off-center fed dipole, which allows you to operate on multiple bands. If you move it so that it's a third on one side and 2/3 on the other. You can have an end-fed dipole, which is where you take the feed line and you put it at the end of the wire. This is very convenient if you're going to take your antenna and throw it up into a tree, because you can have your feed point be near the ground and the top of your dipole, and then you can throw that up into a tree. And back in the 1930s and 20s, when dirigibles were a very common mode of transportation, we had what was called a ZEP dipole, which is a dipole that would be hung off the bottom of a dirigible once it got up into the air. We now call these J-poles, but the antenna structure is exactly the same thing. Lastly, you can take a dipole and you can fold it over on itself and not affect the radiation pattern too much. And this is what a lot of repeaters will use. So a lot of repeaters will have these antennas off to the left. That's a very common looking antenna at a repeater. And if you take these folded dipoles and you put a bunch of them together, that's what a radar installation will use as the antenna for radar. Okay, so if we look at the big picture, we have the current and we have the voltage across the dipole that's rising and falling at the frequency and the wavelength that's being transmitted from the transmitter. So the radiation is launched into space broadside from the antenna. And it looks something like that in 3 dimensions. And when those electromagnetic waves cross another antenna, they will induce a small amount of current to flow in the antenna in time with the radio signals that were transmitted from the transmitter. And that is then fed into the receiver, and that's the way radio works. That's the way antennas work in this overall process. Alrighty, so that's the basic introduction I want to do, and now I'd like to go off on to the questions. Any of the instructors, anything from the chat that we should talk about? No, I don't hear anybody. So very good. So let's go on and talk about the question pools. All right, there's 2 topics in this particular portion of the question pool, which means you will have 2 questions on antennas in your exam. T9A01 says that a beam antenna, think of it as a light beam, it is one that concentrates your signals in one direction. So if you were to take a bunch of dipoles and lay them out on a single antenna, on a boom, what you will notice is that some of the characteristics of light, like there's something that light has that's called a mirror, that you see yourself in the bathroom when you go in. And we have other things that light knows how to work with called lenses that allow you to focus the light in particular directions. Surprise, surprise, radio is exactly the same thing as light, except the frequency is different. The wavelength is different. So you shouldn't surprise you that there should be radio-related things that represent mirrors and lenses, and that's what a directional antenna does. We'll talk more about a Yagi in a little bit, but this is an example of a beam antenna, which is a directional antenna that allows you to concentrate signals in just one direction. If you were to go around your neighborhood and your neighborhood used over-the-air TV signals, you'd see a bunch of TV antennas that looked exactly like this, because that's what you used to put up on your house to listen to TV signals, was a directional antenna like that. Another question, the second question in this area is, what is antenna loading? Antenna loading is when you add inductors to your dipole that make it be longer than it physically is. So if you think about this, if you were designing a dipole for the 2-meter band, each leg is relatively short because each leg is only going to be a half a meter, which is like 1.5 feet long. Very manageable for the 2-meter band. For 80 meters, that's almost a football field in length, where a quarter of that, 200 and something feet, go out one side and 200 and something feet go out the other side. That is a long, long antenna. So what you do is you have it be shorter than 250 feet off of each side, and you put a coil in a coil of wire in the antenna so that it electrically looks longer. And so what happens if you take this dipole that we've talked about and you put it parallel to the Earth? What do the signals look like coming off the antenna? They are horizontally polarized. So the antenna looks like the radiation pattern is coming broadside off of the antenna. Now, this is kind of an unusual question because when you deal with a repeater, repeaters are all vertically oriented. When you think about it, when you hold your HT up to talk to it, your antenna is held vertically. When you put a mag mount on your car, your antenna is vertically. When you look at the dipole antennas that are on your repeater, they're mounted vertically. So off of a 2-meter antenna, you typically would have a vertically polarized antenna. What's a disadvantage to the antenna on one of these little HTs that you would receive, a Baofeng, for example? And it has a relatively low efficiency. The reason why is because it's not a full quarter wavelength. Each one of these little Baofengs that you'll pick up, you'll notice that the antenna is only about 7 inches, 7 or 8 inches long. It's not 19 inches. It's much shorter than that. So the efficiency is not nearly as full as you could with a full-size quarter wave antenna. One of the first things we tell people to do is to go away and throw away or put in a drawer the antenna that came with your radio, and to buy an aftermarket 19-inch full quarter wave antenna and use that on your radio. You'll get a lot better reception and transmit a better signal if you do that. How do you increase the resident frequency on a dipole antenna? You shorten it. So there's an inverse relationship between frequency and wavelength. So if you think about that, an 80-meter dipole that is almost a football field in length is 3.5 megahertz. A 2-meter antenna, which is 6 megahertz. So this also should not surprise you because the speed of light is constant, which means that so the example I like to give is if you were walking next to a small child that walked at a particular speed, and that's no matter how hard you walked, they still walk at that speed, you will notice that you either have to take shorter strides, and you can take them more often. So the stride length is comparable to the frequency. So there's an inverse relationship. If you're going to walk at a constant speed, if you have a shorter stride, you have to pick up the pace. If you have a longer stride, you slow down your pace to be able to talk to a child that's walking at a fixed speed. So that's the way you can reason about these questions. What kind of antenna offers the greatest gain? And the option here is something called a Yagi antenna. This was developed by Dr. Yagi and Dr. Yude back in the 1920s. 2 Japanese scientists discovered that if you put a couple of dipoles together, that it made a directional antenna. So that directional antenna that we talked about a couple of questions ago, that's a Yagi antenna. And Yagi doesn't stand for any initials for anything. It stands for the one of the 2 professors that developed it in Japan. What's a disadvantage of trying to use your little handheld with this little flexible antenna inside a vehicle? Well, the signal strength is reduced because you're in a metal box. You're in something called a Faraday cage. You're inside an environment that stops all the radio signals from coming into your car. So how do you solve that problem? You put an antenna on the outside and you run a feed line into your radio inside the car. But that's the disadvantage of trying to use a handheld inside a mobile vehicle. What is the approximate wavelength in inches for a quarter wave vertical antenna at 146 megahertz? So this is actually a very simple question. Let's work it out. What band is 146 megahertz? Well, we know from our calculations in the first couple of sessions, 300 divided by the frequency in megahertz is equal to the wavelength. 300 divided by 146 is roughly 2 meters. So you're in the 2-meter band. What's a quarter wavelength if you have something that's 2 meters long? That's a half a meter. So a quarter wavelength is a half a meter. How many inches are in a meter? 39. If you take 39 and divide it by 2, because it's a half a meter, works out to be 19.5 inches, and 19 is the closest answer to this particular question. This isn't magic, folks. It's really simple third or fourth grade arithmetic. Okay?
Question.
Go ahead.
Kathy in chat had a question. Is there an image to describe T9A05?
Back. So the way the image, well, so if you want,
Suggestion.
go ahead. So go ahead.
Dave, I was gonna suggest to Kathy, what she do is to get a piece of graph paper and work out frequencies up one side, work the quarter wave antenna lengths on the other axis, and plot the numbers. And it would make it really easy to see what happens when you decrease or increase the frequency.
So if you're a math major, what you could do is you could have the formula that says 300 equals wavelength multiplied by frequency in megahertz. So that's the way we had talked about it before. However, I'm a visual person, and the way I think about it, I literally have a picture of me holding my daughter's hand walking down the street that says the faster I walk, the shorter steps I have to take. Or if I want to take long strides, I have to slow down. So there's an inverse relationship between the two. But if you multiply the two together, it's going to equal 300. And 300, the speed of light is 300 million meters per second. So since megahertz is in millions, you can say 300 equals the frequency multiplied by the wavelength. So if you're a math major, a formula may work. I've seen some people that drew a circle and had 300 at the top with a frequency and wavelengths to the left and to the right in the bottom half of the formula. The other way, again, for me, I just picture in my mind that I'm walking my daughter. So if the frequency has to go up, the wavelength goes down. If the frequency goes down, the wavelength has to go up. Hopefully that works for you. All right, and last point I wanted to make is, oops, sorry. All right, let's go back. All right, the next question is very similar to the one we just did, but it's phrased a little bit different. What's the approximate length in inches of a half wavelength 6 meter dipole? So what's a half a wavelength of 6 meters? It's 3. How many inches, how many inches are in a meter? 39. 3 times 39 is 117. The closest option in the answer is 112. Again, this sounds formidable, but it's really basic, simple arithmetic. Okay. All right, next question. In what direction does a half wavelength dipole radiate the strongest signal? The answer is broadside away from the antenna. The way I like to visualize this in my mind is I think about somebody has a dipole up at their house. And I physically look at that dipole, looking at it from the end of the dipole. And I'm looking down the wire. How much cross section can I see? Also, what I see is the end point of the wire, right? Because I'm looking down the wire. So how much radio is being transmitted that I can see? The only surface area is that little bit where the wire is. Now I go over 90 degrees and I look at the dipole. I think about this being a 80-meter dipole. So 20 meters are on one side, 120 feet. 80 meters on the other side, 120 feet. How much of that antenna can I see? I can see all of that antenna. I'm going to get the maximum amount of radiation pointed at me broadside off the edge of the dipole. That's the way I look at it. Another question, what is antenna gain? It is an increase in signal strength in a particular direction. Now, and there we show the radiation pattern of a Yagi. So a Yagi transmits its signal. Behind the driven element is a reflector that's reflecting all that energy going forward. And then in front of me is a bunch of director elements that act like lenses that focus the energy in a particular direction. Now, there's no free lunch. If you increase the gain in one particular direction, you have to decrease it in others. An antenna cannot generate radio energy by itself. That's what the transmitter does. The antenna can only focus the energy in particular directions. So I think of this as a balloon. You take a balloon, and what happens if you push it from the top and the bottom? It squirts out the edges, right? You're not creating anything, you're just manipulating the balloon so the radiation goes in one direction stronger than it does in others. So the antenna cannot create electrical energy by itself. It can only focus it. With that, what's the advantage of using a 5/8 wavelength whip antenna on your mobile antenna, on your mobile vehicle? And the answer is it has slightly more gain because the 5/8 wavelength whip pushes that balloon a little bit more on the top and bottom. The gain is a little bit more apparent at the off to the sides, to the left and to the right. So if you look at a quarter wavelength antenna, you'll see that it has a very smooth and even pattern that is also pointed straight up in addition to left and right. But since the 5/8 antenna is a little bit taller, it pushes the balloon down a little bit more so it squirts out the sides. All righty, and you'll have one of those 10 questions. One of those will be on your exam. So let's go to the second area. It talks about feed line. So what's the benefit of a load SWR? SWR stands for standing wave ratio, and it is an artifact if your antenna does not match the same impedance of your feed line. When you transmit your radio signal down the feed line, and when it gets all the way to the feed point, when it's going to hit the antenna, some of that, if doesn't match entirely, some of that bounces back towards the transmitter. And the ratio between the forward power and the reverse power is the SWR. Since you're bouncing the power back and forth on the feed line, that will reduce the amount of signal that's actually transmitted. So we want a low SWR, so as much of the transmitted power will actually be transmitted versus bounce back and forth on the feed line and be lost on the feed line. What's the most common impedance in amateur radio coax cables? 50 ohms. That's just a number you'll have to memorize. And what does a coax cable look like? This is what one looks like. Rather than having two parallel wires like the ladder line does, in a coax cable, you have a center conductor that takes one of the signals, and then the shield is typically grounded for the other wire that's sent to the antenna. And the reason why we use coax is because it's shielded. All of the energy has a tendency to stay in the coax and not be radiated out away from the coax. Plus, it's easier to use. So ladder line would get kinks in it. Ladder line, if you ran it next to your gutter in your house, it would mess up the signal. So it was much harder to use ladder line than it was to use coax. And since World War II, almost all radio transmitters have now moved to coax as a way of interface, as a way of the feed line between the transmitter and the antenna. What's the function of an antenna tuner? An antenna tuner matches the impedance of the antenna system to the 50 ohms that your radio wants to see. If the radio sees too much difference between the antenna system and the 50 ohms that it wants, then the radio will turn off. It will protect itself. So if you have an SWR of much more than 3-to-1, most modern radios will turn themselves off rather than be damaged with all that reflective power coming back into the transmitter. And we use an antenna tuner to match the impedance of the antenna system with what the transmitter wants. What happens if the frequency on a coax cable is increased? The loss increases. We'll see that in a minute. That's because most coax cables are not designed for higher frequencies. They're not designed for VHF and UHF. They're designed for lower frequencies. And the loss increases the higher you go up in frequency with coax. If you do have a very high frequencies that you're working with, what kind of connector should you use? You should use type N. And this is what a type N connector is. You'll see it has the center conductor, the little pin right in the very center. And then it has a shield, and then it has an outer shield. So it almost has two shields going through on the connector. And this makes the means that it has less loss at higher frequency. However, most radio connections, particularly here in the United States, use PL259 and SO238. And those are commonly used for HF and VHF frequencies. So the newer radios that go very, very high, like the new ICOM radio that goes up into the microwave frequencies, it has a type N connector on the back of it. A dual band mobile rig that does VHF and the 440 band, that will have an N-type connector on the back of it. And what accounts for signal loss in a coax cable? Number one, water. If you get water into your coax cable, the dielectrics, which is the little foam that separates the center conductor from the shield, will start to deteriorate, and you'll get signal loss between the center conductor and the shield if you get water into your cable. So you should always seal your cable if you can, and seal the connector so you don't get water in it. Another thing that can cause loss of signal is if you have a high SWR. So if you have a very poorly designed antenna that has a significantly different impedance from the 50 ohms that your transmitter would like to see, and you have a high SWR on the transmission line, you'll get more signal loss on the wire. And the second thing that also wouldn't surprise you is that if you put multiple connectors on the feed line, you will get a little bit of signal loss for each connector that you put on the system. There's no such thing as a free lunch. If you put one adapter that adapts PL259 to a BNC, to a type N, and each time you add these little adapters, you're going to get a little bit of signal loss. So the correct answer is all of these things impact your signal loss. What can cause erratic changes in SWR? As soon as you hear the word erratic, you should think about a loose connection, because it means as you're moving the cable around, that could cause this problem. I'll tell you a more common, not related to the question, but another common issue is if you've gotten water inside your coax cable, where the dielectric that is in this coax starts to deteriorate. That will also cause an erratic change in the SWR. Just like if you didn't screw it down correctly and the connector is loose, that will also cause an erratic change in SWR. None of those are on the question, however. The answer on the question is a loose connection. There you go. So we've mentioned that as you increase frequency on coax cable, you get more and more loss. So this question asks, what's the electrical difference between these two different types of cable? RG58 is a very flexible cable, or relatively flexible cable, and it only has one shield on it. And RG213 is a much more rigid cable. And if you look at the loss, particularly at VHF and UHF, you'll notice that the RG213 has roughly 1/3 of the dB, has a 4 dB loss, or less than the RG58. And 4 dB is how much? So we talked about dB yet in the class. So it's a little, so it's 1/4 of the signal between the two. What of the following types gives you the lowest loss in VHF and UHF? The answer is air insulated hardline. This is a very large and rigid cable, and it uses air as the dielectric. It has these little plastic inserts that are used to keep the center conductor and the shield on the outside physically separated. Very, very expensive, extremely expensive. And this is what most repeaters will use between the transmitter and the antenna on the repeaters. It's high quality feed line as you can get. That's air insulated hardline. And what is a standing wave ratio? And it is a measure of how well matched the transmission line is with the antenna or the load. If you can get your antenna to be 50 ohms, 50 ohms to 50 ohms is a 1-to-1 perfect match. And 100% of the power that's transmitted will actually get fed into the antenna. If you have higher than 1-to-1, 1.5, 2-to-1, then less and less power will be actually transmitted, and more will be reflected back to the transmitter. At greater than 3-to-1, then the transmitter will probably shut down to protect itself. So it's a measure of how well matched the transmission line is with a load, in our case, an antenna. All righty, so I'm a little bit over, but I think transition to the next. Any questions in chat that I need to address? Nothing heard? Back to you, Steve.
No, actually, we're heading out to Marty.
Okay, sounds good. Let me get sharing here.
And for the participants, this first section is a bit long. We're just gonna let Marty run. He's not intentionally gonna go over time, but that's probably what's gonna happen.
Okay, can you see the screen?
Yep.
Come on. Wrong screen. Okay. My cat out of the way.
Okay, can you go to full screen mode on yours? For presentation mode, we're seeing the previous slide.
Okay, second here. Come on. Okay, you
I
see
did
the
it.
full screen now?
Yeah, that did it.
Okay, good. Okay. Okay, anyway, this is element T7, practical circuits. There are 4 groups of questions, and you'll get 1 question out of each of the groups on your test. Anyway, I'm Marty, W7MJL from Bellingham. You've got some questions you need to have answered. Just send me an email at this address. Anyway, section T7A is a whole bunch of stuff. Station equipment, receivers, transceivers, transformer amplifiers, receiver amplifiers, transverters, basic radio circuit concepts and terminology, sensitivity, selectivity, and mixers and oscillators, push at the talk, and modulation. So anyway, since we're running a little long, I'll get right into this with question 1. What term describes the ability of a receiver to detect the presence of a signal? Well, you think about the answers there, it's the sensitivity of the receiver. How sensitive is your receiver on that particular frequency? Question 2, what is a transceiver? Well, we've talked about receivers, we've talked about transmitters. A transceiver is a receiver and a transmitter in the same box. Answer A. What is a circuit that converts a signal from one frequency to another frequency? Basically, unless you're double E, you just need to remember that is a mixer. A couple of examples over here, pictures, but generally they're just a part of your radio. Four, what term describes the ability of a receiver to discriminate between multiple signals? An example here is your frequencies, and here's the frequency you want, and here's the frequency you don't want. You want to have your receiver to be very selective, so it only picks up this signal and rejects this signal. So if your receiver is very, very selective, this curve here is really skinny. It has a high Q, they call it. Yep. Question 5. What is the name of a circuit that generates a signal at a specific frequency? None of these really make any sense except for the last one, which is an oscillator. An oscillator generates a frequency at a specific frequency. What device converts the RF input and output of a transceiver to the other band? These are not used very often, but it's a box called a transverter. I'm just going to remember that one. Filters obviously will not do it. A phase converter kind of sounds like something that might do it, but the answer is a transverter. What is the function of a transceiver's PTT input? Okay, PTT stands for push to talk. It's the button on the side of a microphone, for example. That's the most, or a button on the side of your handheld. So it switches the transceiver from receive to transmit and back when the button's released. Number 8, which of the following describes combining speech with an RF carrier signal? You've heard this mentioned before. You modulate your RF carrier with your signal. So the answer is modulation. Question 9 in this section. What is the function of the SSB CW and FM switch on a VHF power amplifier? The answer is it sets the amplifier for the proper operation in a selected mode. The various kinds of transmit modes have different power requirements, and by setting it on a power amplifier, it then optimizes the power amplifier for that mode. What is a device that increases the transmitted power from a transceiver? You can kind of tell an RF power amplifier would be the correct answer. 11, where's an RF preamplifier installed? Well, a preamplifier amplifies the signal from the antenna before it actually gets to the receiver on the radio. So of these possible answers, the one that makes sense is between the antenna and the receiver. So it takes us to section 7B, symptoms, causes, and cures of common transmitter and receiver problems, overload and overdrive, distortion and interference, and RF feedback. basically, these are the questions and answers that help you be a good neighbor so that your radio equipment does not affect your neighbor's garage door opener, your neighbor's TV, for example. So what do you do if you're told your FM handheld or mobile transceiver is over deviating? And basically what that means is it doesn't sound right. And the most common way you can fix that is to talk away from the microphone. Oftentimes, when we first get started in ham radio, we hold the microphone right up to our mouths. You don't ever want to do that. You want to hold it to the side of your mouth and kind of talk across the microphone. That way you don't overdrive the signal. What would cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? Well, if you don't have a problem with your radio, the most common reason is that the receiver that's having the problem is not able to reject a strong signal outside of the band that they're actually trying to receive. Takes us down to 3. Which of the following can cause RF interference? Well, if you overload on the transmitter frequency, if you're over deviating, that can cause some interference. Harmonics can, if your radio transmitter is not designed properly and is transmitting on frequencies that are harmonics of the primary frequency, or if there's something wrong with the transceiver or with the transmitter and it's actually transmitting on the wrong frequency. So all of those questions are actually correct. Which of the following could you use to cure distorted audio caused by RF current on the shield cable of a microphone? For audio frequencies, filters really don't work that well. Preamplifier is really not a good choice, but a ferrite choke, which is a little piece of magnet that attaches around a cable, can help cure that kind of distortion. How can fundamental overload of a non-amateur radio or TV receiver by an amateur signal be reduced or eliminated? The best way is to add a filter at the antenna input of the affected receiver. I've known amateurs that have had complaints from their neighbors, and they've actually gone out and bought a little channel filter like this for their neighbor and installed it between the cable, or installed it on the cable going to their TV. They're only about $25, and it makes you a much better neighbor, helping your neighbor fix the problem. Which of the following actions should you take if a neighbor tells you that your station's transmissions are interfering with the radio or TV reception? Well, first thing you need to do is make sure that your station is functioning properly, and it's not the cause of interference. If your TV is actually being affected by your radio's transmissions, it's likely that there's something wrong with their radio, with your radio. Then you would look at, okay, what is wrong with your radio? Could I put some filters on it? Am I actually having a problem with the transmitter circuitry? Again, it's trying to be a good neighbor. 7, which of the following can reduce overload of a VHF transceiver at a nearby commercial FM station? Basically, again, installing a band reject filter looks something like this. $25 or $30 will oftentimes correct the problem. 8, what should you do if something in a neighbor's home is causing harmful interference to your amateur station? Well, you want to talk to them, try and identify what the problem might be. Politely, which is really hard sometimes, inform your neighbor of that FCC rules prohibit use of devices that cause interference, and make sure that you're not causing the problem. So actually, all of these are correct. One thing that really is causing some people interference is your neighbor who has solar panels on the roof, and the inverters that they use to convert the DC off of these solar panels can generate RF, which can be a real pain if you're an amateur. Fortunately for most of us that operate in VHF and UHF, that's not a great problem, but for high frequency operations, it can be a real pain. What should the first step be to resolve non-fiber optic cable TV interference caused by your radio transmissions? The most obvious cause of filters probably are not going to work. A preamp's probably not going to work. So just make sure all of your TV feed line connectors that are having the problem are properly installed. You as a ham have probably gone in and made sure that your coax connectors are all properly installed and tightened. But it's likely that your neighbor might not have theirs properly installed and tightened. Question 10, what might be a problem if you receive a report that your audio signal through an FM repeater is distorted or not intelligible? Well, it's possible your transmitter might be off a frequency. It's possible that your batteries are low and your signal's not being very strong. It's possible you're in a bad location. So actually, all of those choices are correct. 11, what is a symptom of RF feedback in a transmitter or transceiver? Feedback has nothing to do with SVR. These days, transmitters are very tightly controlled, so you're probably on the correct frequency. blowing fuses is a real problem, but it's nothing to do with RF feedback. So answer C, garbled or distorted or unintelligible voice transmissions are a good sign that you might have a problem. Which takes us to section 7C, antenna and transmission line measurements, troubleshooting, SWR, effects of high SWR, key line failures, and basic coax cable characteristics and use of dummy loads. This is one of the real problems with a virtual class. In in-person class, this is where we would actually bring in some radios, bring in some test equipment, and actually give you students a chance to have some hands-on. But it is what it is, so we'll just struggle through it. Question 1, what is the primary purpose of a dummy load? The answer is A, to prevent transmitting signals over the air when making tests. If you're just playing with your radio, trying to troubleshoot a problem, you don't want to actually be transmitting while you're doing that. Dummy load is a box with a bunch of resistors in it that actually will simulate an antenna, but you're not actually going to transmit out on the air. 2, which of the following is used to determine if an antenna is resonant at the desired operating frequency? The answer is B, an antenna analyzer. Ideally one like this, which is really nice, but costs about $400. But these days you can get these, which are called a NOVNA, which run about $50. And if you're going to get serious about antennas and tuning your antenna to reduce the SWR, these are great investments. What does a dummy load consist of? Well, I mentioned it earlier. It's basically a bunch of resistors inside a device, oftentimes submerged in oil to dissipate heat. And it's set to be 50 ohms, which is the standard impedance of a transmitter. What reading on an SWR meter indicates a perfect impedance match between the antenna and a feed line? Well, you might remember that SWR is a ratio, and the only ratio on this pool of answers is 1-to-1, which is a perfect match. 1-to-1 is really hard to get in real life. So 1.1-to-1 to, let's say, 1.5-to-1 is considered great. 3-to-1 and higher is bad. And by bad, I mean unless your transmitter has protection circuitry, can actually end up with a puff of smoke coming out of your transmitter if you operate at bad SWRs for a length of time. Anyway, which kind of takes us into question 5. Why do most solid-state transmitters reduce output as the SWR increases beyond a certain level? And the answer is pretty obvious based on the pool of answers: to protect the amplifier output transistors. Because seriously, you can smoke your transmitter if you operate at a bad SWR for a period of time. What is an SWR reading of 4 to 1 indicate? And 4 to 1 is a really bad SWR to actually have. It means you really want to tune your antenna somehow, and that indicates an impedance mismatch, which basically ties back to question 5. Question 7: what happens to the power lost in a feed line if you have an impedance mismatch? Well, it's converted into heat, which is the reason that if you operate for a period of time with a bad SWR, that heat will actually be generated in the output circuits of your transmitter and cause damage. What instrument is used to determine SWR? A directional watt meter. I've never really heard that term used in real life. Everybody calls it an SWR meter, but they can look like this or this. If you're serious about radio and get a desktop transceiver, I would really recommend you get one like this. The simpler ones only cost about $60, and they give you a good indication if something is wrong with the impedance match between your transmitter and your antenna. Which of the following causes the failure of a coax cable? This one was mentioned earlier, and it is the most common problem is moisture contamination. You have a connection to your antenna that's outside in the rain. If that's not properly sealed, you're going to get some moisture into your coax, and it's going to cause a failure. Why should the outer jacket of a coax cable be resistant to ultraviolet light? Well, you want to protect your cable. So looking at the answers is the one that kind of makes sense is answer D. In this case, ultraviolet light can damage the jacket and allow water to enter the cable. And again, water inside a coax cable is a recipe for cable disaster. We talked about the air core coax and what's a major disadvantage of the air core coax compared to a foam or solid type of coax, other than and it's very expensive. It's really hard to prevent moisture from entering the cable. You've got to make sure that your connectors are properly connected and they're hard to connect, and you've got to make sure that the connection is properly sealed. I mean, this stuff runs $8 and $9 a foot, so you don't want to mess it up. So if you ever decide to use air core coax, make sure you use it properly. Takes us to section D. Using basic using basic test instruments, voltmeters, amp meters, and ohm meters, and soldering. This is a section where it's really great to do in person because you can actually use the meters. But anyway, question 1, what instrument would you use to measure electric potential? Well, remember, potential is voltage. So the answer is B, a voltmeter. Question 2, how is the voltmeter connected to a component to measure the applied voltage? Well, this one's not obvious, but if you think about it, you're actually going to be trying to measure the voltage across a component. So the answer is in parallel. If I wanted to measure the voltage across this resistor, I'd measure across it in parallel. If I wanted to measure the voltage of this across this load, I'd measure on both sides of the load, which is to be contrasted with question 3. How do you measure current? How's a multimeter connected to a component? And again, if you're measuring current, you're measuring the flow of electrons through that component. So to measure that current, you would put your meter in parallel with the current you want to measure. So I want to measure the current through these resistors. I would put my amp meter in parallel. And it's really hard oftentimes to actually do a current reading, because to put it in parallel, or to put it in series, you've actually got to cut the circuit to actually put your meter in series. So that says, how am I going to do this? Well, that can be a real problem sometimes. There are meters that have a piece of hardware that actually goes around the circuit and can measure the magnetic field of the current that's going through the circuit. But generally in radio, they're not used. Again, what kind of instrument is used to measure current? We just talked about it. It is an ammeter or an amp meter. They're both proper. Question 5 has been removed. Question 6, which of the following can damage a multimeter? This one, if you've actually if you used a multimeter, basically the best way is just to memorize the answer, but attempting to measure voltage when using a resistance setting. A resistance setting on a multimeter actually generates a small voltage that's trying to send through a circuit, and if the circuit's powered up, you're going to fry your meter. So attempting to measure voltage when you're on a resistance setting on the multimeter. Which of the following are made by using a multimeter? You can't really measure strength and noise, impedance, and reaction and reactance are actually AC measurements, and multimeters can't measure those, but you can measure voltage and resistance. Which of the following types of solder should not be used for radio and electronic applications? This one you just want to remember that you don't ever want to use acid core solder when you're soldering a circuit. Acid core solder is used primarily for plumbing applications. Question 9 is hard if you never soldered. It's obvious if you ever have soldered. What is the characteristic appearance of a cold or bad tin lead solder joint? And if you've never soldered, just remember that it's a rough or dull or clumpy appearance. You know, these are bad solder joints. A good solder joint is shiny, and these are caused mainly by not having a good mechanical connection when doing soldering. If you're soldering and the component moves, it'll cause a bad joint. So you want to have a good mechanical connection when you're soldering. What reading indicates that an ohm meter is connected across a large discharged capacitor? Unless you've actually attached an ohm meter across a cap, this one is just basically best to remember that if you attach the meter across a discharge capacitor, resistance is on the meter is going to actually increase with time because the small charge that your meter is putting out is actually charging the capacitor, which increases the resistance. 11. Which of the following precautions should be taken when you're measuring an in-circuit resistance with an ohm meter? Since your meter applies a small voltage to the component that you're wanting to test, you want to ensure that the circuit's not powered on, because you're going to get erroneous readings and you're very likely going to burn up your test instrument. So that concludes the questions that are in these 4 sections. on quizzes
Kathy put a question had there.
I go back here. Get a picture. Okay. On a multimedia to voltage, and there'll be a position to do resistance and a position to do current. So you just have to make sure that, but you have to make sure that it's set to the test you want to make. Hopefully, that answers a multi and resistance, but you have to make sure that it's set to the proper test so you don't fry your meter. Other questions? Okay, I will stop my share here. Just
to John and the ham radio basics part of this.
Alrighty. So two things I wanted. Already share. Let's go ahead this. No, sorry, folks. All right, hopefully everybody can see this. I wanted to talk about, to get everybody a bee in your bonnet, so to speak, to make a decision about where and when you would like to take your technician exam. Because of the geographical locations. I went to the Clark website, and these are all the various exams that are offered. Information there for October if you wish. September, that if you are ready to go, you should go ahead and think about registering for an exam. At the top of the calendar, I put the URL, ham.study/session/Clark information, and you can go about registering for an exam. The exam if you're a full-time student, need is a statement from you, all of the but that for your general and you wish to upgrade, all license that you be ready to pass whatever exams are that you sign up for. So if you, we don't like this, the way I describe it is this is a Yoda-free zone, meaning meaning that you need to be ready to pass to be able to sign up for the exam. We don't allow people to just try. Let's see here. So yeah, so there's a question about how they're done. Yes, we use Zoom to be able to use all the cameras that are available on Zoom, and you will share your screen out, and then you go to a website that has all the exams online, and you take the questions. It looks very, very similar to hamstudy.org. There are practice exams. It's actually done by the same developer that's developed both sites. So, and you answer the questions, and then the software scores your exam. You have 3 or 4 VEs that are in the Zoom breakout room with you, and they observe you the whole time you're taking the exam. So hopefully that answered your question, Kathy. If you had something else, feel free to ask away in chat. So at this point in time, I think folks should be thinking about when they want to take the exam. Right now, we do have an exam scheduled on the September 24th. It's just for this class. However, I typically recommend that if you're ready, you should take the exam. There should be nothing to stop you. Strike while the iron is hot. While you know the question pool, then sign up for an exam and take it. There's really no advantage to delaying. Let's see here. And the second thing that I wanted to mention that I will put into chat is there's a new program that was just been started within the month that QRZ.com and Gigaparts have gotten together and are now offering what they call a Jumpstart program that will give you a Welcome to Ham Radio package that includes a free dual band radio with programming, software, cables, and a goodie bag with other things that several vendors have kicked in to. This is only for new licensees, and it's only available till the end of October. And it is only available if you've been licensed within the last 30 days of making your application. So once your grant date comes up, 30 days from that license grant date is when you can apply for the program and get a free radio. So that's a really nice program, and I will put into chat while John is doing his thing, information for how you can apply for that. It makes no difference where you get licensed. If you get licensed from a class or you study on your own, whether or not you do in person, whether or not you do online, it makes no difference. Just assuming your first amateur radio license is you make application within the first 30 days. So if there are any questions about that, I'll take it in chat. Other than that, that's all I had, Steve. So what we'd like you to do is rather than putting everybody on the spot today, what I'd like you to do is to think about over the next week what exam you'd like to be, your plans are for getting licensed, whether or not you're going to take your exam, whether or not you're going to put it off for a while. You are going to take your exam. What session do you think you'd like to be able to sign up for? Back to you, Steve.
That was good, Dave. Next up is John. And you should be able to share your screen. And this is our
Okay,
ham radio beta.
and I will be doing that right now. Let's see. Ooh. Are you seeing a slide that says amateur radio? I was first licensed fairly recently, 2015. Radio operator at Providence Regional Medical Center in Everett, Washington. And in the past, I was also a radio volunteer at there's a lot of information. Obviously, we're 40 minutes late starting, so we will not be done by 6 o'clock. That's for sure. I expect we will be done by 6:30ish. Understand if people need to bail out early, but it's just the way it has turned out.
Starting now.
First of all, let's see here. Is this working? There we go. The use of amateur radio to support various, talk about the difference between go and public safety radio. Okay. We'll talk about some of the supported agencies that you might want to become involved with and emergency communications groups that support some of those agencies. We'll talk about some of the procedures and skills that are useful in emergency communications. And finally, the use of handheld radios or HTs in emergency communications. So why ham radio? Well, during a major disaster, there's quite likely there's not going to be any power. The internet may be down. The phone lines, both landline and cellular, may not be working, or they may be so overloaded that you really can't access them. Oftentimes, first responders will be overwhelmed and 911 may not be working. The public safety communication systems may be overwhelmed. And you might actually be physically isolated as well, depending on the nature of when Hurricane Maria hit, and they were an island, essentially an island as well, because we could not be accessible. So we always often hear this cliche that when all else fails, there's ham radio. And why do we say something like that? Well, because ham radio doesn't require a lot of that infrastructure that will fail during a disaster. We don't need the internet. We can run our radios on alternate power sources, battery, solar, portable generators. And our equipment, most of it can be portable or mobile, can be moved around to different locations. We have the advantage of frequency agility. We can operate on multiple bands. We can also operate in multiple modes. Your public safety communication systems typically are on a few frequencies and in a limited number of modes that they can operate in. And we have much more agility and flexibility as amateur radio operators. And typically there's a lot of operators in a given geographic area, maybe a lot more ham radio operators than there are public safety operators for their radios. So those are the advantages. let's talk a little bit about how you can personally use ham radio in a disaster. You can use it, first of all, for you and your family to communicate with each other locally via VHF or UHF radios, or if you're attempting to contact family out of area through HF or through the National Traffic System, which I'll talk about in a moment. You can do that either with voice communications, or you could have the ability to do it through email over the radio, through data systems. You can also communicate with your neighbors. Oftentimes, different communities that are particularly isolated communities may form their own neighborhood radio networks, their support systems within that community to exchange situational awareness information, to request aid from each other, and so forth. And it can possibly be used to contact first responders, not directly, but you can contact somebody who can get through to 911 when you can't. So those are some of the uses that you could make of ham radio personally during a disaster. And I mentioned the National Traffic System. This is an important way that you can get health and welfare messages sent out of area to family. It's a service of the ARRL. In fact, it was the original purpose of the ARRL. American Radio Relay League, the word relay in that title was just that. They relayed messages across the country and still do. There are networks set up to do this around the country. So you can get a message passed from one part of the country to another. And when it gets to the end receiving ham, they can call or email or contact the person to whom the message to be delivered. Kind of like old telegrams. In fact, the ARRL radiogram form looks a lot like an old-fashioned telegram. But that can be a vital way to move health and welfare messages during a disaster. But mostly what I'm going to talk about today is how ham radio can support various agencies during a disaster. Both government agencies and non-governmental organizations as well. We can provide a number of functions for those agencies. We can be the eyes and ears of them out in the field to report in situational awareness information. We can be used to shadow officials if they have no cell phones working and officials are out and about surveying the situation. A ham radio operator can shadow them and relay information for them via radio back to their emergency operations center or to other people in the field. We can be used to operate radios at an agency's emergency operations center. We can be used to provide communications from a shelter to a headquarters somewhere or to an EOC. Hams can either be directly involved with an agency, volunteer with that specific agency, or join a group that supports agencies. An example of volunteering with an agency is for instance, a hospital. They may have their own cadre of volunteer amateur radio operators, or the Red Cross or Salvation Army does that. Or you could become a member of an organization that supports one or more government or non-government organizations. And we'll talk about those different organizations here shortly. I'm not going to go through all of these, but I am going to upload at the end here a PDF of these slides. And this has a bunch of definitions of abbreviations and acronyms, of which there are many in emergency communications. Just to kind of take a quick look at these, and as I use them during the rest of the presentation, I'll explain what they are. But this is there'll be a list that'll be in the slide deck that you'll have available after the presentation. So I'm going to go ahead and just skip on through that to save a little bit of time, since you can look at that at your leisure. Okay, differences between casual and emergency communications. And by casual, I mean just your ordinary ham radio activities that you may do. These are not time sensitive. Oops. These are not time sensitive. You can do this whenever you want to do it. On the other hand, with emergency communications, it typically requires timely delivery of messages during an emergency, obviously. Your casual communications, you're usually going to be using your own equipment at your own location, whether it be at home or in your car, but you're going to be using your own equipment at your own location. If you're supporting a an agency, you may be needed to, they may need you to operate their equipment at their location, in which case it may be something new and unfamiliar. So that's a big difference. Casual communications, you can do it at your convenience, and normally disasters don't happen at your convenience. So that's another big difference. Your casual communication allows time for new operators to sort of learn at their own pace. Emergency communications requires trained and skilled operators from the get-go. So that's another big difference. Casual communications, failure is not a life-threatening. If you mess up something up, hey, it's really no big deal. However, failures in communications or inability to relay a message can be life-threatening in an emergency. Also, in an emergency, you might be dealing with both amateur and non-amateur radio operators, public safety operators, and messages really do need to be accurate. If you're just rag chewing on a net somewhere in casual communications, it doesn't matter how accurate the message is, but in EMCOM, it does. And also that you can think of probably of other differences as well. Things like, emergency, you're probably going to be on, like we talked about, temporary power, different locations and so forth. But those are some of the main differences between your casual communications and EMCOM. And there's also differences between amateur radio and public safety radio operations, which you may have to interface with if you're working in support of an agency. Amateurs have to be individually licensed. Public safety, they have their license covers all the users in their organization. Their station is licensed. Hams usually provide their own radio equipment. Public safety operators, they operate their agency's equipment. Hams should have the knowledge and skills to assemble the equipment, troubleshoot it. Your public safety operators typically really don't know anything about the hardware. They know how to turn it on, change channels, and talk on it, and that's about it. Hams are able to program their own radios. Public safety radios typically are not programmable. And also amateurs have, as I mentioned before, have band and mode agility, but public safety radios are typically a fixed band, fixed mode, and operators really can't change any of that. So those are some of the differences. So a lot of different agencies that you might be able to talk about supporting. Tribal governments would certainly be one. It might be through the tribal police chief or the emergency management or manager or some other way it may be organized. State and local governments. Hams can support special purpose districts like school districts, water districts, fire districts. Support the National Weather Service. They have a program for hams to spot weather for them. Civil Air Patrol can use amateur radio operators. Same thing with the Coast Guard Auxiliary. You can probably think of other ones, search and rescue organizations and so forth. So various government agencies. There's also non-governmental agencies that can use amateur radio support in a disaster. I mentioned hospitals and clinics before. Red Cross, Salvation Army has a team called Saturn Salvation Army Team Emergency Radio Network, I think it is. Southern Baptist Disaster Relief, other organizations that do disaster relief often can use ham radio operators. There are also groups that support other organizations. You'll hear these terms quite a bit. RACES, R-A-C-E-S, Radio Amateur Civil Emergency Service. ARES, Amateur Radio Emergency Service. A newer term you will hear is Auxiliary Communication Service. I mentioned I'm a member of Snohomish County ACS, Auxiliary Communication Service. We'll talk about that in a moment. Civil Air Patrol, again, the Military Auxiliary Radio System supports military. Community Emergency Response Teams, or CERT teams, can often do use ham radio operators. And REACT, the Radio Emergency Associated Communications teams, may have ham radio operators for their primarily other forms of radio services, CB, MERS, FRS, GMRS, and we'll talk about those also. RACES. RACES is a radio service. It's not really an organization. It's a radio service like amateur radio, CB radio, family radio service is a service. under Part 97 under FCC rules. Operators and their equipment are registered with the local civil defense agency. Everybody thinks civil defense, that's from the 50s. Well, what they really are talking about these days is your emergency management managers at your various jurisdictions. They are your civil defense agency. On the RACES service, hams may be communicating with non-hams, but they may be using amateur frequencies. So it is a radio service. There is no national group. There's no national organization. Each local emergency manager organizes their own RACES operators, and their credentials are issued by that, whatever that agency is, and they support the government organization. These support government agencies, not NGOs. This is kind of a typical local structure for a RACES group. You have your emergency manager, they'll have a radio officer that works for them, and one or more maybe assistant radio operators and the RACES operators. Pretty flat organization, very flexible. ARES, on the other hand, is an actual organization. ARES, Amateur Radio Emergency Services, is a field service of the ARRL. And it consists of licensed amateurs who have registered their qualifications and equipment for communications duty for public service. And there's a link to the ARRL website for the ARES information that you can get further information on ARES. Generally supports non-governmental agencies, although they can also support government. It has a nationwide structure. It's a national program. It's managed locally, however. There's not really any top-down management per se. ARRL divides the country up into divisions, sections, districts, and those have emergency managers, or they have managers, and they also have they also have emergency coordinators, or ECs, section ECs, district ECs, and so forth. This kind of shows here actually there's a lot of other stuff on this map, but it does show the ARRL sections. There's 71 sections around the country. Depends on the size of the state. Each state will have at least one section for the state. States that have more operators, larger population, tend to have multiple. You can see like in section 5 there in the orange, you can see that Texas is divided into a North Texas, a South Texas, and a West Texas section. But each of the other states there, New Mexico, Oklahoma, Arkansas, Louisiana, Mississippi, they just have a single section. So that's the way the ARRL organizes their sections, and within each section, they'll have emergency coordinators, and under them, they'll have district emergency coordinators, and then under the district coordinators, local coordinators, and then the members of the organization. So it is actually a national structure that you can join. ACS is an organizational concept. It's kind of an overarching management structure that allows emergency managers to combine all these ham radio operators together. They combine their RACES operators with an ARES group, with REACT people, all under one umbrella organization. It's a way of organizing locally. All the communicators are put together sort of in one organization. The state of California, city of Seattle, and many other, as I mentioned, Snohomish County, many others organize this way. Department of Homeland Security has an auxiliary communications course that pushes this model. It's consistent with ICS. We talked about ICS last week. Under the ICS system, these radio operators are called auxiliary communicators, and they report to a communications unit leader. MARS, the Military Auxiliary Radio System, sponsored by the DoD. There's an Army and an Air Force MARS. There is no longer a Navy MARS. There used to be. They use military frequencies. They are similar to, very close to the amateur bands, but they are not amateur frequencies. But they often use amateur radio operators on those. They do use amateur radio operators in support of the military missions. Other groups, Civil Air Patrol, that's Air Force Civilian Auxiliary Program. They use radio operators as well for things like search and rescue, disaster relief. I mentioned before CERT. If you're familiar with the CERT teams, oftentimes they have they are volunteers get specialized training in basic disaster response. to assist when first responders, until first responders can arrive. They often will use amateur radio. They may also use FRS and GMRS radios, which we'll talk about in a second, and integrate ham radio frequently into their communications plans. And I also mentioned REACT, which is they monitor citizens band, family radio service, general mobile radio service, and multi-use radio service frequencies. Last week, you were introduced to NIMS and the ICS, National Incident Management System, and it is a federally required for jurisdictions to participate in or to follow the NIMS and ICS systems to be eligible for federal money. NIMS is core principles, concepts, and processes. They have common terminology and organizational processes. It's a concept that promotes effective incident management. ICS is a component of NIMS, and it describes the organizational structure of an incident. And again, I know this was covered last week, so not going to go into any detail on NIMS and ICS, other than to mention a couple of the main concepts and how they apply to emergency communications. Common terminology, use of plain language is important in communications. Management by objectives, prioritize objectives. Those two are concepts of NIMS. The other three are concepts of the ICS, incident command system. And that's unity of command. Each individual only has one boss. Span of control, try to keep the structure so that one person is not supervising more than 3 to 7 people with an optimum of about 5, and chain of command, which is an orderly line of authority within the organization. So if you're going to be working in emergency communications with an agency, you really need to understand these structures and how they are organized, because we need to fit in to their organization. The days of ham radio operators just showing up and saying, usually with a bunch of HTs with antennas sticking off of them, and hats and shirts with all kinds of logos on them, and and they're coming in. I'm here to save the day. I have a radio and I know how to use it. Those days are over. Emergency managers aren't looking for people like that. They want people that fit into their organization, understand their systems, and work under their standards. So it's quite structured. It's not, and it does require a lot of training and practice to be able to fit in and do the job that these organizations need to have done. Staffing at EMCOM post is a lot more than just sitting there. You're going to do mostly listening. You need to listen to the net control station and other traffic. You need to be able to respond when called, and be efficient when transmitting. Brevity is really important in emergency communications. Brief, concise, clear statements. You don't want to take up a lot of airtime because somebody else may have more important information to pass. You need to kind of minimize the airtime. Deliver the information to and from whoever you're working for. And it's really important skill is to be able to log information. In the EMCOM world during a disaster, if it isn't written down, it didn't happen, and that really impacts the supported organization for getting reimbursed. If it wasn't written down somewhere, it didn't happen, they aren't getting paid for it. So it's a really big issue. Log keeping is a really important skill. And it's also important to not repeat information that people hear, privacy issues. If you're at a hospital, HIPAA issues are concerned. HIPAA is the Healthcare Insurance Portability, what's it, HIPPA, I forget what the other P is, Act, or personally identifiable information. If you're an operator and you're asked to pass something over the air, because ham radio traffic is available for anyone to listen to, anyone can hear it. So personal information should not go out over the air. It's important to let your supported organization, if they ask you to do something like that, to say, well, remember, anyone can hear this and they may want to reconsider doing it. Like I said, most of what you're going to do in EMCOM is listening. Don't transmit unless you actually can add value, have real information to offer. And the other important thing is keeping track of traffic, not only what you send and receive, but keeping track of whatever is going on the net. You might have to take over as the net control station, so you need to understand what's going on, or you may need to be able to provide that information to another person who has to take over as net control, because maybe they came on new, they didn't have that information, and you've been there and you do. But logging is really important. I know I've mentioned that several times, but it is really critical. And being able to listen isn't always easy in a disaster situation, in an EOC or at a shelter or anywhere else. The noise level goes up considerably, and we tend to contribute to that noise level. That's why the use of headphones is often necessary, not only so you can hear better, but so that the noise from the radio speakers isn't contributing to the overall din at the scene. The noise can also cause distraction. Usually people are going to be asked, if you don't have a job there, don't be there. Don't contribute to the chaos. We all tend to sit around and chat a lot in emergency. That doesn't help much. Also, using a handheld may allow someone to roam around to an area where it's less noisy and they can hear better. We'll talk a little bit about station identification in emergency communications. We all learn here on the technician exam, the FCC requirements for identifying every 10 minutes during a communication or at the end of each communication. That does not mean every time you transmit, you need to use your call sign. We tend to overuse our call signs, particularly in EMCOM situations. Saying it more than necessary just, again, adds unnecessary information to the traffic. Also makes it harder for people to remember who's who. You want to stay legal and do it every 10 minutes, or if it's a continuous conversation, which is unlikely, or at the end of your final, as you close your conversation. Often with emergency communications, we're not using our own personal call sign. We're using a station call sign for the entity. They may have a with like a club call sign that's assigned to them, and that would be the call sign that you might be using. And sometimes that's not easy to remember what that call sign is. So, but you might want to think of your FCC call sign as a substitute for saying out at the end. And I'll show you what I mean by that. Here's an example of somebody at an EOC. They put up the EOC's call sign and the EOC's tactical call sign, which we'll talk about next, in front of them so they can remember what it is. Perfectly fine to do something like that. Keeps you from getting confused. A tactical call sign is a word or short phrase that describes the location or function of what you're doing instead of your legal FCC identification. It's easier to remember. It makes on-the-air dialogue easier to follow. When a shift changes, somebody doesn't have to relearn who's this call sign, person's call sign, because you're going to be identifying yourself by your location or function. They don't substitute for the requirement to give your FCC call sign, but they are useful. For example, it might be EOC, shelter, transportation hub, something like that. It's best to establish these ahead of time and include them in the communications plan, but they're extremely useful and really stressed in emergency communications. So here's an example of an exchange with the tactical calls. EOC, this is shelter. Shelter, go ahead. We need 200 cots for our shelter by 5 p.m. today. Copy, you need 200 cots for your shelter by 5 p.m. EOC. K7, HIO. So he's done because he's given his call sign. Shelter comes back, says shelter, K7 MOO. He's done, he's given his call sign. So that's an example of how that's used in EMCOM. The next thing I want to talk about is effective communications. Mentioned some of the things about brevity and clarity, but some of the things important to know are mic skills. And this actually applies not just to EMCOM, but the last presentation that was dealing with talking about overmodulation on a microphone mentioned this. Holding the mic about 2 inches from your mouth, talking across the microphone. speaking in a normal voice. If you yell into the mic, it's going to distort and enunciate so that you can be heard clearly on the other end. Consciously key the mic, pause before you speak. You want to leave ample space between communications in case someone else needs to break in with something more important. And you want to limit your transmission length, dropping occasionally in case somebody else needs to break in. So these are some of the things that lead to effective emergency communications. Think of the PTT, push to talk. Think about it as being planned to talk. Think about what you're going to say before you push that button. Don't key the mic until you have planned what you're going to say. And we all get stuck in the middle, forgetting what we were going to say or getting confused. And that's okay. Just say, stand by, unkey the mic, replan what you're going to say, key the mic, and continue if the channel's still clear. In emergency communications, you should be using plain language whenever possible. Large, complex words, particularly like in a hospital trying to do medical terminology, something like that, can be hard to decipher over the radio, particularly when there's interference. So try to use plain language as much as possible. Again, this is part of the NIMS guidelines. We also use pro words, which I'll talk about next, but we don't use codes or signals of any kind. Q signals, 10 codes, things like that are inappropriate in emergency communications. But pro words and the phonetic alphabet is. And this is the ITU phonetic alphabet. If you're going to work in emergency communications, you should know it. You get people who are, particularly people who like to do contesting and like to make up their own cutesy words for these letters, but that doesn't contribute to clarity and getting the message through. Using the phonetic words that people are expecting to hear does, particularly when there's a really bad signal, a lot of noise going on. These are the words people expect to hear for those letters. So that's the ones you should be using. And pro words are, it's short for procedural words. They're words or phrases that facilitate communication by conveying information in a more condensed, standardized format. They're voice versions of old Morse codes first developed in the 1860s, but their meanings have evolved over the years. There's actually a NATO military publication, ACP 125, that's sort of the authority on pro words, and those same pro words are used in emergency communication. Our plain language is just it's plain language that people know mean a certain thing. Examples of pro words are Roger, over, out. Those are pro words. So those are ones we've probably all heard. You know, out means this is the end of my transmission to you, and you don't, no answers required or expected. I'm done. This is it. Over, on the other hand, it's the end of this transmission to you, but I'm expecting a response from you. So go ahead and send it to me. So over and out are never used together. I mean, it's one or the other, not both, despite what you sometimes see in movies. Roger, another common one, just means I've received your last transmission satisfactorily. Or if it's a radio check, it means loud and clear. Sometimes used to mean yes as well. Those are just a couple of examples. There's many of them, and it's something that people that get involved with EMCOM need to be more familiar with. So the last thing I wanted to kind of cover is talk about using HTs in emergency communications. There's several advantages of HTs. They're very portable. Stick one in your pocket, carry it around. They may actually be more likely to survive the disaster than your base station at home, because the antenna may come down, whatever may happen. You know, the power supply gets fried somehow. So it may survive when the rest of your communications gear doesn't. So those are a couple of pretty good advantages, especially the portability. But there's some disadvantages to using HTs. Short range is one of them, and that's due to a couple of things. Your typical antenna that comes with your basic antenna that comes with an HT is usually not very good. You also are operating with a low antenna height because it's in your hand. It's not like it's on the rooftop somewhere, right? They also have low power, typically not more than about 5 watts on an HT. They also have limited battery life, so that battery is not going to last terribly long if you're transmitting a lot. So those are some of the disadvantages. However, those disadvantages can be mitigated substantially. Look, you can change your location. You can go up, you can improve your antenna. You can increase the power output. You can get other power sources to replace your dead battery. So location, just like buying real estate, it's location, location, location. You want to be away from signal absorbing objects, particularly metal objects. Sometimes if you just turn around, you might get a better signal because your body may be shielding some of the signal, again, because you're holding this in front of your head to talk usually. You might just be able to step a few paces one direction or another to improve the reception by improving your location just slightly. You can find a better spot. If you're indoors, go outdoors. If you're in a car, get out of the car. If you're in a car with an HT, you're inside a big metal box. Not ideal. You might want to move your antenna higher. If you have a speaker mic or a headset attached to your HT, you can hold that radio above your head so your antenna has more height, sort of a Statue of Liberty pose with your HT in the air. That can improve it. Go up to the roof of a building. Or if you have to stay inside a building, go to a higher floor near a window. You might get better reception. If you're outdoors, go to a higher location, a hilltop. Doesn't have to be very high, just a little bit higher location could substantially improve your reception. Replace the rubber duck antenna. This is probably the best thing you can do initially is replace that antenna with an aftermarket better antenna. This will usually be the best thing you can do initially. This is an example of one. A lot of people go out and buy the Baofangs that then you can buy an aftermarket. Their antennas are terrible. So you'd want to get an aftermarket. This is an example of one that I happen to have. It's a lot longer than your little rubber duck that comes with the radio. It's longer. It's also better. There are many others that you could get. If you're going to be operating in a vehicle with a handheld, you could put a mag mount antenna on the roof of the vehicle and attach your handheld to that. It gets the antenna outside the big metal box that you're in. It also gets it higher up. So that can substantially improve the performance of your HT. HTs don't work real well inside cars. Another thing you can do is add a tiger tail or a counterpoise to your radio. Basically a piece of wire about 19 to 20 inches long on a dual band HT. Put a ring connector on one end and you can screw the antenna onto it so that the ring is making contact with the ground or the shield side of the antenna only and not the center pin. And that will basically give you a dipole, a more effective dipole. That's another way to improve your antenna. You can connect your HT to some sort of external antenna. This is an example of a J-pole that somebody could be attached to. It could be on a mast somewhere that you actually connect an HT to, or any other radio for that matter. This is a really useful little one for emergency use. A roll-up J-pole. It's an example here on the right of one that you can buy for about $20, which you could probably make it for less, but it's a lot easier to buy. And this is made out of 450 ohm ladder line that you roll up, and then you can unroll it, hang it from a tree or some high place, connect your HT to it, and you'll get a whole lot better reception. So there are a number of things you can do to improve your antenna. You can actually make an antenna out in the field out of coax if you needed to. That's another way to get a better antenna, and find some way to hang that up, just like you would do with the J-pole. Now, this would be limited to a single band here, but you could do that as well. Increasing power. Well, the simplest thing is make sure you're on the high power setting. That would help. You can also get amplifiers that you can connect your HT or other to make amplifiers for your mobile and base stations. But for an HT, where you've got just 4 watts in, you could get 35, 45 watts out with an amplifier. That's another option. For backup power, you'd always want to make sure you have several spare rechargeable batteries for your HT. Also, you should have a charger, and if you happen to have your batteries that way. Another option is some number of radios you can get this little clamshell case that replaces your normal rechargeable battery with a packet of AA or AAA batteries, usually AA batteries. Then when those go dead, you can just get a bunch. It's usually easier to find more AA batteries than it is as you can get an adapter that'll allow you to remove the rechargeable battery, insert this adapter arrangement, and plug it into the cigarette lighter of a vehicle and power the HT that way. You can also connect it up to some sort of an external 12-volt battery is another option. Portable generators can provide power for recharging your batteries, or you may be able to plug in directly to a 12-volt outlet on your generator. Similarly, you could have set up portable solar panels is another way. All of these can overcome the shortcoming of low battery life on an HT. So these are other options. If you're interested in emergency communications and getting trained along those lines, these are a couple of things a couple of resources here. FEMA has a number of online courses. If you're going to get involved with an MCOM organization, they're almost always going to require that you take at least these first 3 ones, IS 100, 200, and 700, 800, which is a little more advanced. Oregon ACES is an excellent basic course in emergency communications. That's their website. It's a lot of hands-on with it, actually programming radios and so forth. ARRL has an Introduction to Emergency Communications course, EC001. You can go to their website to find that. I mentioned that OXCOM course. That's a little more advanced than either of these two, either the Oregon ACES or the ARRL course. So would recommend taking those first and then OXCOM. It's a little hard to come by. It's not offered a lot, but it's a good course. And there are a bunch of other online free courses that you can take through FEMA's Emergency Management Institute online. Just a ton of them on various emergency management and communications related subjects. That's it. Unless
Getting all this. So thank you, everyone. Thank you for the. So we don't have anything else, so unless there's questions, everybody's free to go. And thank you again.
Thanks,
All right.
everyone.
So Ray, I think you can shut it down.
All righty, I'm going to end the meeting. Thanks, everyone, for being here.
We'll see you later. And that incident was kind of interesting.
Yes, I just couldn't resist phrasing it in that manner.
You're breaking up a little bit. We'll see you later.